Hi everyone, and welcome to today's webinar, which is making the case for adaptive reuse of reinforced concrete slabs in buildings using LimitState SLAB. I'm Tom Pritchard, I'm your host for today, and I'm joined by Professor Matthew Gilbert, who is going to speak to you shortly. Today's webinar is going to last about 30 minutes. There's a Q&A interface available, so if you do have any questions that you wish to ask throughout the webinar, then please feel free to type them in, and we'll have some time at the end that we can spend actually answering those questions for you. If we don't get around to all of the questions, we will follow them up at the end with sort of email responses, so don't worry too much about that. I think what I'll do is I shall pass you over to Matthew shortly.
Thanks, Tom. Thanks, everyone, for joining us for this webinar today. So, just first of all, just give you an outline of what's going to be covered today. I'm basically going to introduce you to the topic and also the technology, and then Tom's going to take over, giving you a demonstration of the software, including a case study. We'll then wrap up with a summary and opportunities to answer any questions you might have. So, in terms of the big picture, and the case for adaptive reuse of existing buildings is very, very clear. A very significant chunk of carbon is effectively released when we build a new building. Just the structure that's used is very, very important before we come into any matters of operational carbon. So if we can refurbish and upgrade existing buildings, then typically we're talking about an order of magnitude less embodied carbon than demolishing and rebuilding. And given the climate emergency, really it's no longer an option to basically continue with business as usual. We've got to change. Bit of context, looking at the UK perspective, lots and lots of codes of practice were used in the past. A similar situation arises elsewhere. But in the UK, we had various codes of practice that then were discontinued, and Eurocodes took over. The key thing is that a lot of the methods were conservative. So if we use elastic principle stress design or the Hillenburg strip method of design, for example, then we're talking about conservatism. More recently, there's been a sort of fashion to use elastic finite element analysis to design concrete slabs. Now, these methods, unfortunately, are prone to provide over-conservative predictions of strength. However, the silver lining is that we have hidden reserves of strength in buildings that were designed using these methods. And so there's an opportunity that we can take advantage of that when we come to reusing an existing structure. Potentially, there may be a lot less strengthening, for example, if any, at all, than we might originally expect. So technology that Tom's going to be demonstrating through application of LimitState SLAB is called yield line method. Yield line method was developed probably about 100 years ago now. I think the first paper was in 1922. It's a simple, direct means of establishing the collapse load of a concrete slab. And it's widely accepted that it leads to more realistic assessments of slab, certainly than elastic methods do. The downside of it, however, is that it's non-conservative if you choose the incorrect mechanism. So on the right-hand side of this slide, we've got lots of possible mechanisms for a particular set of scenarios. If we miss the correct one, then we're going to end up overestimating the capacity. And that's where technology that LimitState SLAB uses comes in, called discontinuity layer optimization, or DLO for short. This is a technology that was developed less than 10 years ago, described in several papers as indicated on the screen. But basically what it does, it takes the guesswork and the worry out of the yield line method. And we can solve this actually as a very simple in mathematical terms, linear optimization problem. So how do we go about that? We have our slab, for example, a square slab with fixed supports. We populate that slab with nodes. We then interconnect those nodes with potential yield lines, and then we use optimization to find the critical arrangement of yield lines, the minimum energy solution. And that's basically what's happening when you solve a problem using limit state slab. So without further ado, I'm going to hand over now to Tom, who's going to give you a demonstration of that software.
Thanks, Matthew. So what we're going to do now is examine a couple of examples of yield line analysis using limit state slab. And we'll begin with demonstrating how the method and the software work with a simple example, and then we'll move on to a more complex practical case study of adaptive reuse. So one of the first things you want to be looking at is the confidence when you're exploring any analysis methodology. So you want a valid and credible solution. So here we're going to take a look at a worked example that's described in Kennedy and Goodchild's book, Practical Yield Line Design. This was published by the Concrete Center in the early 2000s. And if you're interested in learning more about yield line analysis and design, then I would thoroughly recommend that you seek out a copy of the book. It's very useful. And what we'll do is we'll show that one can very easily obtain the same results as example hand calculations provided in the book, but also that we can move far beyond the constraints associated with manual yield line design and therefore employ the method to our benefit in the context of adaptive reuse. So the problem that we're going to be looking at itself is a rectangular corner bay of an above ground floor slab with stiff beams around the perimeter and with a 250 mil thick C40 concrete slab with isotropic reinforcement. And we know that it has a moment resistance of M and an ultimate load on that slab of 20 kilonewtons per meter squared. And the question that we're asking here is, what's this required value of M that's required in order to prevent collapse? And so it's a pretty straightforward design question. And in Kennedy and Goodchild, the first thing they do is they postulate a very simple hand calculation, which is an envelope shape, such as this. And for simplicity, they started with a symmetric one. So that's what we're going to do with limit state slab. And what they did, they worked out that they had one geometrical unknown, which is beta, and they needed to determine what the value of M was. And they found that was just below 37. So we're going to do the same thing within limit state slab. And we can see here, actually, what I've done is predetermined those yield line positions. In a minute, we're going to look at it without predetermined yield line positions. But we can see on the left-hand side here, we have a structural definition, which is yielding slab. And I've entered the same value as Kennedy and Goodchild found for their value of M for those yield line positions. So if I solve, what we see here is actually it's following the yield line pattern that we've already predetermined, and we've got an adequacy factor of 1. And basically that's saying that the structure is just in equilibrium with the applied loading for the conditions that we've provided. So for those support conditions and for those material properties and the loading. And that's basically just to prove that we can get the same solution that Kennedy and Goodchild were getting by hand, very, very simply. If we go back to the presentation, we can see, obviously, yes, a moment capacity of just under 37 kilonewton meters per meter. But it's obvious that the support conditions aren't symmetric, and as such, the yield line pattern itself is unlikely to be symmetric. So Kennedy and Goodchild go on to consider a more complex envelope with 3 geometric unknowns, so the 3 betas here, and work out that with this postulated failure mechanism, actually the required moment of resistance is about 38.5. And we can do that too very easily, simply by just moving the yield lines in the software and solving again to see if the adequacy factor goes up or down. So if I just unlock here, I can quickly just select that part of the structure, solve again, and we can see here, actually the adequacy factor has gone up. So it's a little bit higher strength with that one, but I can also move it down here and solve again, and it's just below 1. So from this, it's clear that if we more closely capture the true mechanism failure, that the required moment capacity is above that original 37 kilonewton meters per meter that we found initially. And therein, like Matthew said, lies the issue. If we don't capture the true collapse mechanism closely enough, then we underpredict the required moment resistance for the applied loading. And that's where the automation comes in. So with SLAB, we can quickly and easily do away with the trial and error and just home in right to the critical mechanism, and one that's often far more complex than you'd ever want to be trying to analyze by hand. So that's what I'm going to do here. If I just go to this problem, we can see that here we don't have any predetermined yield lines in the problem. We just have one full slab with a value of just over 40 for the MP. And if I click solve here, what we'll see is that process that Matthew outlined earlier. So the nodes, the potential yield line positions, and the software going through using the optimization to determine what the critical collapse mechanism is and the associated adequacy factor. And we can see here that actually the top left of it is pretty much that envelope mechanism that Kennedy and Goodchild were postulating, but around the corners at the top and bottom, we also have these fan mechanisms, and that would be a lot more time consuming to analyze by hand. And we can see, as I said, that the MP value that we're looking at now is actually a little higher than we originally looked at. So the actual critical mechanism is like that. Our critical moment resistance that's required is just over 40. But how does that then lead us into adaptive reuse? What are the benefits of being able to determine the critical collapse mechanism and the corresponding ultimate load with a higher degree of accuracy? Well, if you imagine that an existing building has slabs that have been designed elastically, like Matthew was saying, or perhaps using the strip method, and we know what the properties of that slab are, then we can use this automation of the yield line method, the flexibility of the software and the precision that it provides to work out whether that slab then will have these sufficient reserves of capacity that it can withstand any proposed modifications to the usage. And in Kennedy and Goodchild, they extended this example to include a partition wall along the middle of the slab, which I guess would be representative of a very basic adaptation of the building. So we can do that ourselves as well. So if I unlock here, what we can do is very quickly, these purple icons at the top just allow us to add different types of load. And I want to add a line load. And if I do it right across the middle here, you can see I've actually already defined it previously in the software as 20 kilonewtons per meter. I apply that and we can see that we have this line load across the middle as well as the pressure loading that's applied to it. Now, we know previously that our adequacy factor was 1 when our moment resistance was just over 40 kilonewton meters per meter. So now we can see what the effect of having this additional partition wall load on it is. And if I click solve, it will go through the same process again and tell us what the solution is. So we can see here, after a few seconds, we get an adequacy factor. Now, what was 1 with this extra line load on is now 0.826. So from that, we can work out that our moment resistance needs to be 40 over 0.826 in order to provide enough resistance to that line loading. And we can also animate the failure mechanism in order to see how that slab is responding to that loading. So effectively, if we knew that in our existing building, we had a moment resistance of 50, then we would be able to also take into consideration that line load. So that was a very basic example. The old line method is automated, so there's no need to worry that the critical pattern has been missed. We can determine the true capacity and also ascertain whether existing structure is strong enough for proposed modifications. We can quickly and easily check for the influence of modifications. So we said elastic FEA could be an alternative, you would argue, but then there would be a need to make adjustments for things like column perimeters, and there would be no redistribution of moments, so a danger of underpredicting the capacity. And as Matthew alluded to, many slabs in buildings have been designed using many different methods, and we want to ensure that we're able to make the best use of those slabs, irrespective of that method that's been used. So we'll jump in now to a case study of adaptive reuse. And this is an example that's taken from real life a few years back. And as you'll see in many city centres at the moment, the building owners wanted to repurpose an open plan office block as an apart hotel. And rather than demolishing a building and completely rebuilding a new structure in its place, there are obvious economic as well as environmental benefits to being able to make modest changes to what's already there. And as part of the process, the engineers had a number of questions that arose from this proposed change of use. So firstly, is the slab strong enough to be able to withstand the loads imposed during the construction of this change of use? And those loads are primarily imparted through scaffolding and props and the like. And second, once the renovation is complete, what loads can the slabs withstand so that the stakeholders in the project can then set the layout of the apart hotel, maybe providing a gym space, a restaurant area, that type of thing. So having a better idea of what the actual capacity of the slab is in particular areas in order that you can then set it out as necessary. And you can see here that the original plans either weren't available or didn't have the required information on them. So an SI was undertaken, which determined the properties of the slab. So we see it's isotropic with an MP value of 145 kilonewton meters per meter. And there are actually two parts to the slab that was being investigated. There was the slab itself, which was 225 millimeters thick, and there was the beam, which is a bit thicker at 600 millimeters, both of them made from C28 and 35 concrete. And on the right-hand side here is just an image of the outside of the building before these works were undertaken. Here we can see one of the areas that is being investigated. In this case, it's at the far corner of the building, and this blue area here outlines the section to be modelled within LimitState slab. And here's the plan of that corner. On the left-hand side here, we have the area of interest. The blue square here is one of the columns that you saw on the previous slide, and the yellow line is that beam section that runs throughout the slab. On the right here at the top, we have an outline of the construction loading, which takes the form of both point and line loads. And at the bottom, there are a few sketches from the site investigation. So if we jump back into the software, we can see here is the LimitState slab representation of that corner of the slab with the yellow part, which is the beam. We have the column, and we also have the slab to either side. On the left-hand side here, we have structural definitions. So we have the slab itself with the 145 kilonewton meters per meter MP in both directions. And then we also have the strip itself, which is the beam. And obviously you can see here that the MP value for that in the vertical direction is much higher. If we look into this is the load case manager. We can see that we have defined two load cases, the first of which is the one for construction loading, And we can see in the table below, we have, as well as the self-weight of the slab itself, we have the pressure loads from the construction and the services, as well as a number of line loads for the supports and point loads for where the reactions from other parts of the scaffolding are coming through. We also have additional columns from the floor above, so dead and live loading that's being applied from them. In the second load case, we're more interested in the in-service reaction of the slab. So we have things like the finishes, the services, and what we've sort of loosely termed apart hotel loading, but as pressure loads, as well as those two column loads from the floor above. And what we can do with the software is solve those two particular load cases and determine whether or not the adequacy factor is above 1 in each of those load cases. We can also see that we've added ULS partial safety factors into our problem. So if I solve this problem, what we see is that the software first off looks at load case 1, goes through, works out what the critical collapse mechanism is and the associated adequacy factor on that loading. And then similarly, if I go to this second one, actually the failure mechanism is very similar in both cases, but it does the same for the second in-service loading as well. And again, what we can do is we can animate that solution to get a better idea of how the structure is reacting. And we can see here at the bottom, we have an adequacy factor for both of those load cases. For load case 1, it's 1.453, and for load case 2, it's 1.601. And the implications of that we'll discuss shortly. So if we come back here. So the two questions we were asking, firstly, is the slab strong enough for the construction loads? And the answer to that is yes. We determined that the adequacy factor was 1.45, which means that the loading in the construction load case needs to be about 45% higher to cause collapse under the construction loading. We can see here the line loading and that response there. And question 2 is what loading can the slabs take post-renovation? And we determined the adequacy factor was 1.6 in that case, which means that the loading there needs to be about 60% higher in order to cause collapse under the post-renovation in-service loading. So there might be some scope there for changing how parts of the slab are being used, like say whether you want to put a gym or a cafeteria or something in there. And the features of LimitState slab that were used in this particular case, we had the multiple loading scenarios all in the same file, so the construction and the post-renovation. We had user-defined partial safety factors, and we also had application of different types of loading, so pressure, line, and point loading. So that's a very brief introduction to how LimitState slab can be used for adaptive reuse case studies. Just to quickly summarize, we've shown you that you can quickly demonstrate the real flexural capacity of reinforced concrete slabs in existing structures, and that establishing the real capacity is likely to reduce the amount of intervention that's required in your building. The underlying automated yield line technology is, as Matthew showed, is a proven and robust technology from over 100 years. And the software is easy to use. You can pick it up and use it straight away. And you can learn more about this at our website, LimitState.com/slab. So we've come to the point where we can answer a few questions. We've got a few minutes left just to take those. So if you do have any that you would like to ask, please feel free to ask them in the Q&A interface that's in front of you. So we had one question just about how columns are modeled in the software. I think the second example there had one in it, but I didn't really explain how that was modeled compared to the rest of the supports. So on normal boundaries, we can apply different types of support conditions. If we look in the property editor, which is on the right-hand side of the screen here, we can see in this case, this boundary we've got has a fixed edge, but we can select from free, fixed, simple, and also symmetrical and partially fixed, which are slightly more advanced conditions. Where we come to look at a column, we actually have one in this corner here, and we have one in the middle of the beam. All we're doing is, if I select here, we can draw a polygon. Is effectively making a small cutout of the right dimensions and then selecting the boundaries around the edge and applying those same support condition types that we were having for the external boundaries. So in this case, if we wanted, say, simple support around that edge, and that provides column support within our slab, and we can do the same on the edge here. If I just undo that, so we go back to there. Another question, can you look at skew reinforcement? And the answer to that is yes. So if I select the slab structural definition on the left-hand side here, we can see that actually we have two angles that we can introduce into this structural definition. In this particular case, we're just following the normal Cartesian directions, but you can add in obviously an angle of your own choosing. So effectively you determine the line about which the moment is acting, and you can add that angle in that there. Actually had time for maybe one last question. Is it possible to consider moving loads in the software? So we've shown static loading so far. The answer to that is yes, you can apply moving loads. I'll try and do it here very quickly for you. So actually what I'll do, I'll put it into an entirely new slab. So we'll just have a default rectangular slab like this. If I select a point load and put it on the left-hand side here, just say unit point. Okay, we can see that that's represented there. What we can do is go into that load case manager that I showed previously. We can select in this list here the point load, and we can copy that, and we can see here we can offset that point load or that load case by a particular distance. So in this, by default, we're looking at x equals 1, y equals 1. So if I make 4 copies of that, what we would expect is for that point load to move diagonally upwards to the right. I click OK, and we can see now we have 5 load cases, and actually it's gone off the slab there. But yes, that point load is moving diagonally upwards. And then if I solve, the software will go through each of those different load cases and determine which is the critical mechanism in each case. And in this case, load case 1, where we have the point load and the uniformly distributed load on the top of it, is the critical case. So that's brought us to 1 o'clock, so it's the end of the webinar. I'd just like to say thank you again to Matthew for talking us through the technology and the reasoning behind using LimitState SLAB for assessing structures for adaptive reuse. We will make a recording of this webinar available on our YouTube channel over the next few days, and we'll send out an email to tell you when that is available. There are also other webinars that will be taking place throughout the year, so please do keep an eye out for those. They'll be discussing LimitState SLAB and other software and the different features of them. So we do hope that you'll be able to join us at one of those. So yeah, without, I think we should say goodbye. So yeah, please do keep an eye out for those emails. And if you need to get in contact with us, then please feel free to send us an email at info@limitstate.com, and we'll be more than happy to talk to you. So see you next time. Thanks for joining us.